Hello everyone, my name is Jonathan Lenoir and today I will present you some results on the relevance of microclimatic conditions for species distribution models. So first of all, what do I call microclimate? So here microclimate is not a specific spatial resolution or specific temporal resolution. It's more a mix of spatial temporal resolution that will be tailored to specific organisms. For instance, if you are interested in modeling the distribution of an understory or forest-dwelling species, you might be interested in the operative space that is here below the tree canopy, which is the understory microclimate. And this operative space, we call it proximal microclimate, without referring to specific spatial temporal resolution here, but we will define it according to the focal species. Then you might be interested in air temperature, surface temperature, soil temperature. So here is an example of surface temperature for forest ecosystems, where you have temperature at the surface of the bark of a tree exposed directly to sunlight at the forest edge versus the temperature that is on the other side of the tree, which is much lower in the forest ecosystems. And so this is one specific case of temperature, microclimate temperature. What I'm talking about for this specific talk will be more air temperature at a given height, so at 1 meter above ground, here in the understory of this tree canopy. So this is the operative scale I'm talking about here for this proximal microclimate. And macroclimate is the temperature as measured by weather condition, by weather station, sorry. So for instance, if you have the microclimatic temperature as measured by weather station, it will look like this. So this red oscillation over time could be days, could be season, could be several years. But in the understory, the temperature fluctuations are much lower. They are buffered. And this buffering is due mostly to several processes. One is the physiological process, which is due to tree transpiration, the water going through the roots of the tree and towards the atmosphere, and will cool down during the summer the temperature inside the understory. And there is other underlying processes, of course, like canopy shading, but also windbreak. But tree transpiration is one of the main processes during vegetation season, for instance. And so these processes will affect the temperature inside the forest, and the difference can reach more than 2 degrees and up to 8 degrees, depending on which bioclimatic context you are talking about. For instance, if we are in a tropical forest, this temperature difference between inside and outside forest will be much higher than in temperate forest or in boreal forest for maximum temperature during the day. So this is something to consider also. What is the bioclimatic context you are considering for your study? And so far, species distribution models, the toolbox to forecast biodiversity changes, they do not account for these microclimatic processes. So the state of the art in SDM is to use the BAM framework. So BAM for B with biotic, A abiotic, and M for movement. So those are 3 sets of variables that are used as predictor in SDMs to predict species presence absence. So the occurrence are encapsulated within the overlap of this Venn diagram here, where you have abiotic, biotic, and dispersal limitations that are converging in the same space. So this will be the state of the art, and usually relying on ambient air temperature conditions. So for instance, if you fit species occurrences presence absence data to ambient air temperature, you will get an SDM, and then you can increase temperature to simulate temperature change and increasing temperature given a scenario of climate change. And you can check whether the species will shift its range towards different locations where you have, for instance, local extinction at the rear edge and range expansion at the leading edge. But most of the time, these SDMs will tend to overestimate these changes with local extensions that are usually overestimated. So the idea is to incorporate the microclimatic processes via statistical models. So for instance, for forest microclimate, we can use some drivers like tree canopy conditions, topography, and then model the offset of temperature. So the difference between inside and outside forest condition. And this offset, when it's modeled and gridded, you can use it and adjust the climatic grid of ambient air temperature. For instance, could be data from the WorldClim, CHELSA, or Terra Climate databases. And then you get something that is near surface temperature condition. So here, understory temperature conditions, that will be the proximal microclimate of interest for forest dwelling species. And this should correct this overestimation from traditional SDMs. So there are some hypotheses underlying this phenomenon for SDMs and the inclusion or the incorporation of microclimate. And one of the key papers that introduced these important processes and implication for SDM is from Harwood and colleague in 2014 in PNAS. So I'm going to skip this diagram, which is a bit complicated, and we'll show you a simpler version. So here, let's say you have macroclimatic condition as measured by weather station and at a very coarse spatiotemporal resolution. Here, 1 kilometer resolution as given by the WorldClim database. You have a forest patch in green, and the same forest patch, but using microclimatic condition at, let's say, finer spatiotemporal resolution, and which you have a different condition below the canopy. This is temperature below the canopy inside this forest patch. And for a species that is occurring inside this forest, then the temperature response curve or the climatic niche, if you want, for this species might be very different if you fit your SDM with this data of macroclimatic condition versus this data of microclimatic condition for the same species occurrences here in black dots. So the black dots shows the occurrence of the focal species of interest. Here it's a fern that I use as an example. And you will get a different response curve. And we hypothesize, we assume that under using SDM based on and relying only on macroclimatic condition, we tend to overestimate the climatic niche width of the species compared to what you will get with the SDM fitted and trained with microclimatic temperature data. And with potentially a shift of the optimum condition that the species is experiencing below the canopy, that should be lower in terms of optimum temperature as perceived by the species in this operative space of understory temperature condition. So that's the hypothesis that we want to test in this specific work. And so to do this as a material methods, we rely on several sets of bioclimatic variables at 25-meter resolution for each layer that incorporate microclimates through both topography and canopy features. So those are the traditional bioclimatic variables, but they have been produced at 25-meter resolution across Europe only for forest ecosystems. And they have been produced also on a long-term average over 30 years, just like the bioclim variable of WorldClim, Chelsea, and TerraClimate, for instance. So here you have Bio1, mineral temperature, the mean diurnal range, Bio2, and so on. And so those are the bioclimatic layers we can use and compare to traditional bioclimatic layers from WorldClim or Chelsea. And this is the idea of this exercise. We did a comparison, and for a fair comparison, we derived 3 sets of predictor variables to fit our SDMs. One will be macroclimatic layer at 1 by 1 kilometer resolution, like the WorldClim or Chelsea database here. So this is a 1 by 1 kilometer resolution. And then we have microclimatic condition at 25 meter by 25 meter resolution, which is a climatic grid I just have been showing you for Europe. This is an example here with the forest of Compiègne in northern France as an example, to compare with the 1 by 1 kilometer resolution over the same temporal period of a 30-year average. And then we have tried also to compare micro and macro at the same resolution. And so we aggregated the microclimatic layer at 1 by 1 kilometer to get a resolution that is similar to macroclimatic layers, to also test whether this is a resolution effect that will impact the species response curve in our SDMs. And then we selected 6 variables. 2 are temperature-related variables: maximum temperature of the warmest month, Bio5, mean temperature of the coldest month, Bio6, and then we have 2 precipitation-related variables: minimum precipitation, Bio12, and precipitation seasonality, Bio15. And then 2 soil-related variables: cation capacity and soil clay content. Of course, these 4 ones, they don't differ between the 3 sets here. We always have the same set of precipitation and soil variables for all 3 sets of macro, micro, and aggregate. But the 2 temperature-related variables will change according to macro, micro, and aggregate spatial resolution. Then, to fit our SDM, we use species occurrence data from GBIF. Here is an example of Paris quadrifolia as a forest understory species. in Europe. So the black dots represent the occurrence of Paris quadrifolia throughout Europe, our study region here. And you can see that we did that for 140 forest understory plants for which we could retrieve a sufficient number of occurrences across Europe to train our SDMs using micro and macroclimatic conditions. Here is just, you also can see the output of Paris quadrifolia in terms of probability of suitability or habitat suitability based on our SDMs. We use Maxent here to predict the probability of occurrence of this species across Europe at 25 by 25 meter resolution. And so the results of this study have been showing more or less that for 92% of the studied species, so the 140 species I was just mentioning, microclimatic grids, they systematically improved model performance according to one specific metric, which is the CBI, but we tested many other metrics. But continuous Boyce index is clearly the most interesting index here to use because it's based on presence-only data, which is what we use here with the Maxent modeling. We used pseudo-absences and we actually selected an equivalent number of pseudo-absences to the number of occurrences we used. And so the continuous Boyce index will better measure the ability of the model to rightfully predict occurrence without necessarily focusing on the absence, because it's not the point here. We don't have good absence data to check whether the model is good at predicting the absences. But we want to test how good the model is to predict occurrence and presence based on independent dataset. And what we have been showing is that this CBI index presents much higher positive difference or negative difference for, here, the effect size. So we here use a pairwise difference in CBI values for each of the 140 species between the three sets of SDMs. So macro versus the aggregate, so this is microclimatic at 1 kilometer resolution. Macro minus micro, which is micro at 25 by 25 meter resolution, and then aggregate minus micro. And what we can see is that each time, comparing macro to microclimate, either aggregate or not aggregated, gives better, higher performances and positive and negative values here. So much higher CBI values for the microclimatic SDMs, as well as for the aggregated microclimate SDMs compared to macro, which is this case. So in any case, and it's also better to use microclimatic at 25 meter resolution, than at 1 kilometer resolution, as we can see here. It's also improved the CBI index compared to the aggregate. So this is another way to show it here and to show the same results. Here is basically a spaghetti plot showing all 140 species. So one gray line is one species with three different sets of variables we use in our SDMs, the macro at 1 kilometer, the aggregate microclimatic condition at 1 kilometer resolution, and then microclimatic condition at 25 by 25 meter. And you see that the mean CBI increase substantially with CBI at micro being the top CBI value. Here I made a mistake, so this one is micro and this one is aggregate, so 0.28. Sorry for this mistake. So we have much higher SDMs performances when we incorporate microclimatic conditions. And then when we look at the effect of these microclimatic conditions on the species response curve as predicted by our SDMs, we can also see that it affects a lot the actual species response curve. So here is an example for Paris quadrifolia again, with the two variables of bio5 and bio6 that we use in our SDMs. And you can see that here the density values of the different occurrences that have been predicted show that microclimatic layers, so the prediction from SDM with microclimatic condition at 25 meter by 25 meter resolution, provide here a range of values that is much narrower than what we would get with macroclimate or with an aggregate version of microclimate here in the dotted lines. Same for bio6, which is a maximum temperature of the warmest months. We also show a shrinking of the climatic niche. So this is just for Paris quadrifolia, but we did it, of course, across all 140 species. And the outcome is approximately the same as for Paris quadrifolia. Here we have minimum temperature of the coldest months bio6, maximum temperature of the warmest months bio5, and here we have the percentile of the position of the different niche parameters. So here the lowest percentile of the niche along the temperature gradient, so the coldest extreme of the niche, and then here the 95 percentile, which is the warmest limit or the higher thermal limit of this species response curve, and then the optimum condition. And so those are difference, pair difference between the 140 species that we studied. And again, we have macro minus aggregate, macro minus micro that are the most interested for us. And those two, each time they show exactly the same pattern. So here, for minimum temperature of the coldest month, microclimates tend to have a position of the coldest margin that is much towards a warmer condition at the cold margin. Same for the optimum. The optimum is shifted toward slightly warmer condition for the minimum temperature of the coldest month. And also for the maximum thermal limit, we have a shift toward higher values. But when we look at the width, so the thermal, the niche width in temperature, it's narrower with the microclimatic layers compared to macroclimatic condition used in SDMs. And for maximum temperature of the warmest months, we have a bit different results. It's almost the opposite. We have a larger niche width with microclimatic conditions than we're using macroclimatic condition. And also the optimum is slightly shifted towards colder condition when using microclimatic condition for this maximum temperature of the warmest month, which is here temperature extreme towards the warmer extreme. And then finally, about the results, we also with these SDMs made predictions, and you can see also the impact of those predictions for Paris quadrifolia again, with panel A showing macroclimatic layer at 1 kilometer by 1 kilometer, B microclimatic condition aggregated at 1 kilometer by 1 kilometer resolution. There is already some differences, but we see also that the 1 kilometer by 1 kilometer resolution makes things a bit different than if we use a 25 by 25 meter resolution, which is a microclimatic layer here in panel C. So depending on the layer we use, of course, the predicted spatial distribution of the species will differ. And then, of course, run shift will be affected by this. If we compute run shift based on this versus this, even if we incorporate microclimatic condition in both cases, it will give you different outputs, given the spatial resolution is very different between those two outputs here. And so the conclusion of this study, more or less, are these 4 bullet points that accounting for microclimatic processes in SDMs will imply that you will increase the model performance for your understory species. Could be forest plants, but could be also other kind of understory forest species. It will unveil the true realized climatic niche of understory species. You will see here, you have seen here that it affects a lot the position of the optimum and the thermal limits. So using microclimate could give you a more realistic climatic niche for this understory species. It will also better anticipate species redistribution under climate change because you will be much more closer to the realized climatic niche using those microclimatic layers. And it will provide insights to optimize forest management actions based on these outputs from these SDMs. So the take-home message in the end for you is microclimate is indeed integral to the species niche concept and needs to be incorporated in SDMs to anticipate species transition, especially so for this example I'm giving here of forest understory species like forest understory plants. It will affect a lot the outcome of the SDM exercise, especially for estimating and anticipating the biodiversity redistribution under future climate change. So if I come back to the BAM framework of the niche concept with biotically, abiotic, and movement set of variables, then the intersection between those three will be not enough to capture microclimatic condition, and you can more or less assume that microclimatic facilitation, for instance, due to tree canopy here in forest ecosystems, will be depicted in this piece, or this part of the band diagram, where you have where you have dispersal limitation and biotic conditions that are suitable, but the biotic condition, we alter the abiotic condition of temperature to make it suitable. So it's like an extension of the abiotic condition here given by macroclimatic condition only. But because of the, for instance, the tree canopy, which is a biotic component, it will affect the temperature as perceived by your focal understory species. And this is more or less how it expands the abiotic climatic space through a complex interaction with biotic conditions from vegetation here from tree canopy. So that's it for my presentation. And I would like to thank all my co-authors, and especially Stef Haesen, the first author, Eva Grill, and Koenraad van Meerbeek, who lead that study here on the relevance of microclimate for forest species distribution modeling. Thanks for your attention, and I'm happy to take questions. Goodbye.